Now that we're comfortable rewriting logs to an exponential form or an exponential to a logarithmic form, and we're comfortable condensing logarithms together, the next step is to start solving some equations that involve these two inverses. Sometimes you're given an equation where it's already in a log form, and you just need to condense those two together. More than likely, it will be in an exponential form, and you'll have to rewrite to a log form and then continue the process. And you could use a logarithm base of your choice. You could do a log base 10 sometimes, and sometimes you can use a natural log. You're going to specifically want to use a natural log when you have two different bases, and we're going to look at that one last, and those are definitely the messiest of the three. So back to the first one that's kind of already set up for you. I have a log base 5 of x plus 6 plus a log of x plus 2, and that's equal to 1. I have my two logs, so I want to be able to write log, that word, just once. When you are writing log just once, then you know that your logs are condensed, and you can begin that take the log of both sides or raise up to one base from the both sides process. So we have these two logs that are connected using addition, and so I can squeeze these two together using the multiplication rule. So this is going to be a log base 5 now of x plus 6 times an x plus 2. This is equal to 1. I have one log, so I can begin the rewrite process. The textbook and many other videos will say that you're going to raise these both up from the 5, like this. And so log base 5, or 5 log base 5 is a 1, and then of course you'll have 5 to the 1 over here. I normally think of it as just rewriting from my logarithmic form back to my exponential form. A log is an ugly way to say an exponent, so 5 raised to the first power is equal to x plus 6, x plus 2. So there's my base, and this is my exponent. My output is the piece I have out here. We'll then need to clean up whatever my situation is out on the right-hand side after the rewrite, right? That piece that was inside the logarithm. Very often you'll be left with something that you're going to need to distribute. And now over here, when we distribute, we're going to be left with a quadratic because I'll have x times x, x times 2, 6 times x, 6 times 2. And as soon as you see something that is x not to the first power, right? X to the second, x to the third. There's only one way to solve these. You set them equal to 0 and you hope that they factor. Normally, if you're working with textbooks problems, these will factor, just to save you some time so you don't have to use quadratic formula. But in the real world, of course, they do not need to factor. I'll have a 0 after I subtract the 5 from the left, x squared plus 8x plus 7 on the right. Conveniently, that does factor. Factors of 7 that when you add them you get 8, of course, is x plus 7, x plus 1. And now you're going to use your zero product property as if you were starting with a quadratic equation. So x plus 7 is equal to 0. Maybe x plus 1 is equal to 0. And I get x equals negative 7 and x equals negative 1. These are my two possible solutions. Much like when you have radical equations, you can wind up with extraneous solutions. So you need to check your solutions for logarithms. If you go back to the very original, to the very, very top, when you plug in these numbers, are you left with a negative number on the inside? If I plug in a negative 1, I get a 5 and a 1. So no, both those numbers are positive. X can be equal to a negative 1. But if I plug in a negative 7, I'll have a negative 1 over here and a negative 5 over here. You cannot take the log base of a number cannot have a negative on the inside. You cannot have a negative number on the inside of your logarithm. So anything that creates a negative number on the inside is an extraneous solution. And so I need to reject this negative 7, and only a negative 1 is a part of my solution. So no negatives inside logarithms. Just like you won't want to have negatives underneath your radical symbol. If I have something that's not already in log form, I need to isolate the piece that has the exponent. So I'll subtract 5 from both sides. And I have 16 raised to the n minus 7 equal to a 19. I'll look to see if I can rewrite the number that I'm left with on the right-hand side so that it matches the base. 19, there's no way to rewrite 16 raised to a power to give me a 19. So that means I need to rewrite this in log form. You can either take the ln of both sides. In this case, I'm just going to rewrite this from a log or take the log base 16 of both sides. So log base 16 will give me a 19 when I raise it to the n minus 7. So if you have an exponential, you're going to want to go to a log. If you have a log, you're probably going to want to go to an exponential. Now, I don't know what log 16 of 19 is, but I have the change of base rule. So I can say log base 10 of 19 over log base 10 of 16 and get that number by using the log button on my calculator. Log of 19 divided by log of 16. Now I get a 1.06 about. So I'm going to write 1.06 down here. But when I begin the process of now solving, I'm not going to type that into my calculator. I'm going to leave the full decimal on there. And now when I go to add 7 to both sides, when I hit plus, it knows to automatically go to the last thing that I typed in, take that number, and then add 7 to that. And so that I get 8.0619. And it will tell you where to round. I'm going to go to the hundredths for this time. And then so that's my n. I can go back up to the top, see if that is okay, and it looks like everything will be just fine. When you start with your exponential form, you tend not to generate any kind of extraneous solutions. It's only when you start off with log forms. So let's say I have kind of like a double exponential, right? I have exponents on both sides that have variables, and I can't rewrite the bases, and so they match, right? There's no way to write 2 raised to the something that would be equal to a 7 so that I can just do the work on the exponents. So these are going to be the longest ones that you're going to have to deal with. And when you have something that has 2 different bases, we're going to have to use an ln because you can't do a log base 7 on one side and a log base 2 on another. You have to take the same bases on both sides. So we're going to say the ln on both sides. So now I have ln of 7 raised to the x minus 3 on the left and ln of 2 to the 2x plus 1 on the right. Natural log is just an ugly way to say log base e of something, right? And so I have a power to a power rule here. So I'm going to take my x minus 3 and it's going to come out up front. And I'm going to take the x plus 2x plus 1 and put him out front there. But I'm going to put it in parentheses like this. Now I'm going to distribute. But I'm going to leave the ln behind the number and the x like it looks like over here. So I wouldn't say ln 7 times x. I'm going to say x ln 7 minus 3 ln 7. So that way the x and the 3 don't accidentally sneak their way inside of the logarithm as I'm writing this. I'm going to do the same thing on the right. So I'll have 2x ln 2 plus ln of 2. And now the idea is to get my x's on one side and then all my numbers on the other. Stuff without x's, I guess I should say. So I am going to subtract the 2x ln of 2 over this way. which way you go doesn't really matter. So now I have x ln of 7 minus 2x ln of 2. And I'm going to add the 3 ln of 7. So that over here, I have ln of 2 plus 3 ln of 7. At this point, you're thinking, this looks worse than what we started out with. But we're actually really close now. We can factor out the x. See how both of these have just an x? So I'll say x as my greatest common factor, ln of 7 minus 2 ln 2. Leave the right-hand side alone. Anything with a logarithm that doesn't have a variable is just a irrational number. So ln of 7 is just a regular number. It's not a very pretty number, but it's just a number. 2 ln of 2 is just a number. Anything without variables can be typed into the calculator as is and generate a value. That means it's just a number. So ln of 7 minus 2 ln of 2 is about a 0.6-ish, but you can't just round off wherever you want to round off. So what we're going to do is we're going to leave this as a package number. So instead of saying, oh, it's about a 0.6, we're going to leave it just like this and divide that off on both sides. The whole thing. Anything over itself is a 1, and so x is ln of 2 plus 3 ln of 7 over ln of 7 minus 2 ln of 2. So what the heck does that mean? It means if I figure out what this number is and I plug it in for x, that's where these two curves are going to intersect. So let's get an approximate value for this number. Numerator is ln of 2 plus 3 ln of 7. That's my numerator. Divided by denominator, ln of 7 minus 2 ln of 2. And I get about an 11.67. So if I were to graph my original, the 7 to the x minus 3 and the 2 to the 2x plus 1, those two curves are going to intersect when x is about an 11.67. I can check this by going into my calculator and letting one of the sides be y1 and letting the other side be y2. I'll need to play with my calculator screen a little bit in order to see the curves. There's one, and I don't even see the other. Oh, here comes the other. Now we know we're crossing at a little over an 11, and this goes up to 10. Gosh only knows what the y is. I'm going to try and figure out what that y value is by changing my table set to ask. Oop. And go into my table, and I'll put in an 11, and I'll put in a 12, and we are talking about a really big number. So this little e says take this decimal 7 places to the right. So I would have 404 and then 5 zeros. That's what my max y needs to be so that I can see what's going on. So when I go to my window now, I know I'm crossing somewhere between the 11 and the 12, so I'm going to make this, how about a 13? And my y max needs to be really big. So let's say 404. 1, 2, 3, 4, 5. And we'll make the y scale maybe like 1,000. When we hit graph, there's our first curve of the 7x. And here comes the 2. So you can see that there's something turning inside of here. And so I'm going to zoom in just a little bit, right about where my x is an 11.6, if I can. That seems like it's pretty good. Let's try that. And so it's still a little hard to tell, but we can use second trace to bring up calc and look for our intersect. Hit enter for the first curve, enter for the second, and take a guess, which does not need to be terribly good. And there you go. And it intersects at 11.67. So you might be saying, if I can use the graph, why would I go through all the trouble of solving this algebraically? Well, the calculator is only a tool. You'll see all the work that we had to do to try to get to the point where we're verifying where these two things intersect. The calculator is only going to help you verify if you know where to look. Granted, these numbers were much bigger, so if the numbers were smaller, it may be a little bit easier to manipulate the variables and see the screen. But you'll need to know how to use the two to know when you can rely on the calculator and when you can't.